Unit 2, the atmosphere, for day 8 of class. Learning target 2.f, predicting weather, and this will be about our weather fronts. So, learning target 2.f, today we'll be able to use a graph to determine our relative humidity, identify a warm front, and identify the weather conditions associated with it, and identify a cold front, and identify the weather conditions associated with it. So for review, humidity is moisture in the air. Water is present as a liquid and a gas in the atmosphere. The amount of water vapor in the air is called our humidity. The amount of water vapor the air can hold depends on the temperature of the air. Warm air can hold a lot more water vapor and cold air cannot. So when we look at our relative humidity, remember this is what we're going to measure using our psychrometer. This is going to tell us how much water vapor is in the air compared to how much it could hold at that temperature. It's shown as a percentage, and the higher the relative humidity is, the more likely precipitation is. So if we look at these little bubbles over here, at 30 degrees Celsius, okay, we have 28% relative humidity. This is how much water vapor. Now, if we keep the same exact amount of water vapor over here, but we drop the temperature, we notice now we have 52% relative humidity. Again, keeping the water vapor the same, but dropping the temperature again down to 10 degrees Celsius, I've reached 100% relative humidity. Okay, this is what we call our dew point. So for this much water vapor, my dew point is 10 degrees Celsius. In other words, this is the temperature that my gas, my water vapor, is going to start turning into either a solid or a liquid, either snow or rain. So we can graph this, okay? So our dew point is the temperature at which water starts to condense out of a particular air mass. In other words, it's going to start turning into either water for rain, or it's going to start turning into ice or snow. Okay, this changes only when the humidity changes. The higher the dew point, the greater the humidity is in the air. Okay, so if we look at this and we say our air temperature is 25 degrees Celsius, okay, and we say our dew point is around 58, okay, it's going to take me to here, my green line. My green line means I am at 50% relative humidity. If my air temperature is 60 degrees Fahrenheit and my dew point is 60 degrees, I'm at the black line, which says I'm at 100% relative humidity. That means I would expect there to be rain at those temperatures. Okay? So 40 degrees Fahrenheit and around 40 degrees Fahrenheit for my dew point. Again, 100%, I would expect to have rain falling. So our weather fronts. All our fronts are an area where two air masses with different temperatures and densities collide, but don't mix. They don't mix because the densities are so different. Okay? This is what's going to cause our storms and noticeable changes in the weather. We have four basic types of front. We have our cold front, our warm front, an occluded front, and a stationary front. So our first one, our warm fronts. This is going to be our surface boundary between a warm air mass and a cold air mass that it's moving faster than. In other words, this warm air is moving faster than the cold air, so it's going to sneak up on it and catch it. Right where these meet on the ground is my warm front. Okay? Again, the air masses are not going to mix because the densities are so different. Warm air is going to rise over our denser, colder air. In other words, this is much more dense, than this air. So it's going to go over top. This is going to produce clouds and precipitation well ahead of our surface boundary. This is when we have long time rain events where it rains all day. That usually means that a warm front is approaching. So when we look at the temperature associated with a warm front, before it's cool, after, right at the contact of the front, it's all of a sudden much warmer, and then afterwards it's warmer. Pressure is going to be decreasing steadily, and then it's going to level off, and you're going to have a slight rise followed by a decrease afterwards. Our winds, south to southeast before the front. Remember, this is from where they're coming from. Okay, contact with the front, variable, so they're going to be all over the place. And then after the front, they're going to change from the south to being from the southwest. Okay. Precipitation, before the front, we have either shower, snow, sleet, or drizzle. Right at the contact with the front, we have light drizzle, and afterwards, none, usually clear skies. So when we look at our types of precipitations, it's going to depend on the variation of temperature in the atmosphere. So when we're looking at this is our freezing line. Okay. All the water vapor in clouds is usually ice particles. It's not liquid, it is ice particles, because remember, it gets colder the further up you get in our troposphere. Okay, so these are usually ice particles. Once it drops through our freezing line, it melts and turns into rain. It's going to turn into rain, but then if there's a little bit of warm air or cold air at the surface, it turns into freezing rain. So it falls as a liquid, but then at the surface, it's going to freeze on contact with the surface. Again, if there's even more cold air it's going to turn into sleet. So it starts off as ice, melts into rain, and then falls as sleet. Over here, it's never melting back into water, so it just stays snow all the way down. The other type of precipitation we have is hail. These are going to be large ice pellets caused by strong up and down motion. In other words, you have to have freezing as it's falling, and then the winds are going to be so much that it's going to pull it back up, and it's going to collect more rain, and it's going to freeze even more. Okay? Those are only associated with very large thunderstorms. So our cold fronts. This is where our surface boundary between a cold air mass and a warm air mass. Okay? So our denser, colder air mass is literally going to push underneath our warm air. Okay? As it's doing this, it forces that warm air up. Now, because the warm air usually is going to carry moisture with it, okay, it's going to create our thunderheads. Okay? This is where we're going to have thunderstorms that pass. They're going to move much faster than our warm fronts. So these are going to be where you have an hour of rain. It's not going to be all day for our rain. So our temperatures, before the front, it will be warm. Contact with the front, it will all of a sudden be much cooler. And then cold and getting even cooler after the front. With pressure, it decreases steadily before the front, levels off at the front, and then increases steadily after the front. Our winds, they're either from the south or from the southeast before, variable at the contact, and then from the west or from the northwest after the front. Before the front, you might have showers. Contact with the front, you have heavy rain or snow, sometimes hail. Afterwards, you're going to have showers, then clearing. Our stationary fronts. This is going to be the surface boundary between two different air masses with different densities, but neither is moving. In other words, you could have warm air on this side, cold air on this side. Because the densities are different, they're not mixing, but neither one is moving on the other one. Say the warm air is moving in this direction and the cold air is moving in this direction. Last one is our occluded front. This is when a cold front catches up to a warm front. This can cause extremely stormy weather. Okay, so you have your normal cold front and it's lifting up a thunderstorm here. You have a warm front just ahead of it, and you have your long-term rain event in front of this. Okay, so once this cold front meets up with the warm front, you still have the thunderstorm and your long-term rain. Once it finally gets occluded completely, okay, you're going to have this big mess of storm clouds up in the atmosphere.